Whether you accept evolution as fact or not, I think you can at the very least agree with me when I say that just about everything develops somehow or somewhat over time. It's just an inevitable part of life. You, as a person, go from a tot to a teen to an adult. Your mind also develops over this time. The same things happen with other living creatures and even non-living objects like rocks, which are shaped over time by the forces of nature. Therefore, nature also evolves in a certain way, and the nature of the universe is such that it underwent several stages of evolution, if you will, over its lifetime. These major stages, the radiation era, recombination epoch, and reionization, will be covered right now. Another lesson covered the very first few minutes of the Big Bang and the process of nucleosynthesis. Nucleosynthesis is simply the formation of new atomic nuclei, which happen right after the Big Bang and much later on within stars. Anyways, after the era of early nucleosynthesis, radiation dominated the universe. In fact, the stage of the universe's development where radiant energy would have had a much larger density than that of matter is known as the radiation era. During the radiation era, the universe was really hot, way too hot for atoms to be stable. Basically, if a proton and electron combined to make an atom during this time, that atom would be ripped apart almost right away by a really energetic photon or because of a collision with another particle. Additionally, the gas in the universe was very opaque during this era because the hot temperatures forced the gas to be totally ionized, and thus the electrons in the gas were not attached to any nuclei. Well, such free electrons are really good at either absorbing or scattering radiation. That means visible light, a form of radiation, would not make it far from wherever it was emitted in the very early universe, hence the opacity. If you could fly through the early universe, it would be like moving through a thick but bright fog on Earth. The particles of water in the fog would be like the free electrons in the early universe. You could have the headlights on, making it quite bright immediately around you, but unless someone was really close, they wouldn't see you due to the scattering of light. This radiation era lasted from the moment of the Big Bang to about when our universe turned 50,000 years old. After that, the density of radiation became permanently less than that of ordinary matter. However, it took about 400,000 years after the Big Bang for the temperature of the universe to fall enough for the universe to become transparent to light. Here's how and why this happened. First, the universe expanded enough to spread the free electrons far enough apart so that light could travel further and further without being scattered. This would be like thinning out a dense fog. I'm sure you know that in a thin fog, light from headlights can travel much further. Secondly, as the temperature dropped around this time, radiation and collisions no longer had enough energy to break apart neutral atoms that had formed from the combination of nuclei and electrons. Unlike the ionized gas from before, atoms cannot scatter or absorb radiation nearly as well. That means that when these neutral atoms formed, electromagnetic radiation, including light, could travel throughout space with a lot more freedom than ever before, rendering the universe basically transparent to light. I like to think about this process as the following example. Picture a parking lot lined with cars, our nuclei. In between the cars are lots of people, our free electrons. If you tried to make your way past such a crowded mess of cars and people, you'd likely get pushed back or deflected or scattered every which way. But if the electrons combined with the nuclei to make atoms, if the people entered into the cars, there would be now a lot of empty space for you to use to glide right past everyone without being deflected. This stage of the universe's development is known as the recombination epoch because electrons and nuclei combined to form stable atoms. It's also known as the decoupling epoch because light finally broke free from matter during this time. The recombination and decoupling epoch can be summed up as follows: the time when the universe became transparent to light, allowing it to travel for great distances. All light prior to this time period was destroyed after being emitted. This means we can't study the first 400,000 years of our universe using electromagnetic radiation. However, almost all the radiation that was emitted after the decoupling epoch is available for your viewing pleasure as cosmic background radiation. After recombination occurred, the universe continued to expand and cool. This resulted in something called the Dark Age of the universe, a period where the glow from the Big Bang shifted into infrared wavelengths, meaning the universe expanded into complete darkness thereafter until the first stars and galaxies were born and gave light to it once again. This leads me to the fourth and final important change coming after the Dark Age, which began about 400 million years after the Big Bang. It is called the reionization era, the stage in the development of the universe that marks the end of the Dark Age and the beginning of the age of stars and galaxies. This era bears such a name because the first stars that formed in our universe would have been very luminous, very massive, and of short lifespan. The very first stages of massive star formation would have then produced so much ultraviolet light that it would have ionized a lot of neutral gas, or reionized the previously neutral matter in the cosmos, hence the name, the reionization era. After the early nucleosynthesis in the first minutes of our universe, the universe entered the radiation era. The radiation era is the stage of the universe's development where radiant energy would have had a much larger density than that of matter. During this era, no stable atoms could form, and the universe was very opaque. As the universe expanded and cooled, it became more transparent, and stable atoms could form. Thus, the universe entered the recombination epoch because electrons and nuclei combined to form stable atoms. It's also known as the decoupling epoch because light finally broke free from matter during this time. The recombination and decoupling epoch can be summed up as follows: the time when the universe became transparent to light, allowing it to travel for great distances. As the universe cooled and expanded even more, the visible glow from the Big Bang itself faded into infrared, and the universe thus expanded in darkness. This resulted in something called the Dark Age of the universe, a period where the glow from the Big Bang shifted into infrared wavelengths. Then, about 400 million years after the Big Bang, the universe entered the reionization era, the stage in the development of the universe that marks the end of the Dark Age and the beginning of the age of stars and galaxies. And so, there was light once more.